Hey y'all, today we're going to be talking about how to draw covalently bound molecules using things called Lewis diagrams. In order to do this though, I want to talk about a couple of things off the bat. First of all, I want you to be aware of the fact that the process that we use to draw Lewis diagrams is a wonderfully effective process to get the correct Lewis diagram in the end, but it is not representative of the ways that molecules are actually formed in the first place. All right, so we're going to be moving bonds and electrons around in this process. Just be aware that even if we're doing that in this process, it is not representative of what is actually happening at the molecular level. The second thing is Lewis structures, although wonderful, still have their limitations. So they're not perfect representations, and they do have limitations to some extent. We're going to talk about that a little bit as well. But let's go ahead and get started. I'm going to start by giving you guys a technique, a skill of steps that we can use to draw correct Lewis structures. And then we're going to show how to interpret those structures to make sure that they are drawn appropriately. So let's go ahead and get started. Let's start by talking about how to draw Lewis structures. And again, one thing to be aware of is that Lewis structures are wonderful representations of what molecules will look like, but the process that we're going to go through here is not the actual process that molecules take when they are formed. Okay, so just be aware of that. Lewis structures are very good at representing this, but they're not perfect. So I'm going to give you the steps, and we're going to start with step one, which is counting all the valence electrons of all of the atoms within the compound. All right, so valence electrons can be counted very simply. If you're in group 1, you have 1 valence electron. Group 2, 2 valence electrons. You move over to boron, and the group of boron has 3 valence electrons. Underneath carbon, they all have 4 valence electrons. Nitrogen and down, 5 valence electrons. Oxygen down, 6. Fluorine and down, 7. And finally, the noble gases all have 8. So those are the number of valence electrons that these atoms are going to start with. We're going to add together all the valence electrons of all of the atoms within the compound. That's step 1. Step 2 is going to be to identify the central atom. Now, when we identify the central atom, what that means is that we are going to look for the least electronegative atom, with the exception of hydrogen. Hydrogen won't be a central atom. So in general, the central atom is going to be the least electronegative atom in the compound. And be aware that there are some compounds that will have multiple central atoms. We'll address those a little bit later in a different video. Step 3 is to draw the ligands. Now, these ligands are actually the atoms that are going to be attached to the central atom. Generally speaking, it's all of the other atoms in the compound that we're going to be drawing. So we're going to need to draw these around the central atom. Step 4 is going to be to connect each of those to the central atom with a single bond. That is going to be represented by a single dashed line. Be aware that those single dashed lines represent a covalent bond that entails 2 valence electrons. So what we've essentially done with each of those single bonds is we've removed 2 valence electrons from our need to include list. So if we started with 24 valence electrons, we've just used a certain number of those. Okay, so what I like to do is cross out the valence electrons that we've used and write the new number later. It generally helps me to keep account of how many electrons I've used and how many I still need to show. Now that plays a big role in step 5, where we have to complete the valence shells of all of the ligand atoms. So remember, atoms have different numbers of valence electrons. All right, generally speaking, it's either 2 or 8 valence electrons, and normally the ligands are going to either have 2 or 8 valence electrons. So know how many valence electrons to fill the valence shell of each atom. And then what you're going to do is you're going to simply add that number, all right, until the atom reaches its full valence shell. So if the atom already has a single bond, which it does because of the fact that we added the single bond to the central atom first, understand that if we were to say have fluorine, where it needs 8 valence electrons to fill its shell, we need to add 6 more valence electrons to do that because the bond already includes 2. One thing to remember when you're drawing these electrons filling the valence shells is that electrons are paired in orbitals. So we're actually going to draw these as electron pairs. And normally we think of it as sides of a box. So if you drew a box around your atom, you would show a pair of electrons on the top, on the side, on the bottom, and then obviously the bond to the other side or to the other corner. So again, the specifics of that are less important, but them being paired is important because that's a true representation of how orbitals are formed. Now, this is where we get a little bit tricky. If there are still electrons that remain that you haven't accounted for, and again, you need to make sure that you're accounting for every valence electron that you first counted in step number 1. If there are still valence electrons that you have not accounted for, those are going to go onto the central atom. All right, again, in pairs. And don't worry, we're going to talk about this a little bit more in a later video when we get into the specifics of some oddities when it comes to Lewis structures. Now, finally, we need to understand that not all of the atoms will have a full valence shell even after you've added all the valence electrons. This means that we need to do something which defies reality, but it's good for this model process. Remember, this is not what is happening in actual molecules. What we're going to do to create a full valence shell for all atoms is we're going to start moving electrons from atoms that have full valence shells into multiple bonds. So that would be a double bond or a triple bond. We show this with additional dashed lines, just like we did with a single bond. All right, so a single covalent bond is 1 dashed line, a double covalent bond would be 2 dashed lines, and a triple covalent bond would be 3 dashed lines. And we do this in order to fill the valence shells of every atom. And again, this is not what is really happening in nature when a bond is formed. It's not like atoms are moving from one atom to the other in this same kind of manner. Okay, so be aware of that, please. The final step is going to be to recognize that if we have an ion, we need to make sure that we put brackets around the ion and its charge in the top right corner. It's a really important step to understand that we are modeling the representation of molecules, but sometimes polyatomic ions are modeled as well, and those have charges. So we need to represent those charges appropriately. So that's all the steps, 8 steps, which are going to entail a pretty much comprehensive ability to draw any Lewis structure you might be presented with this year. We're going to, in this video, focus on simple Lewis structures, and then in future videos, we're going to focus on more complicated Lewis structures as we go. We're going to start by looking at a very simple Lewis structure, and that's going to be methane, CH4. Now, methane is a simple Lewis structure because there's not too much to it. The first step, remember, is to count the number of valence electrons. Now, valence electrons, in this case, carbon has 4, and each hydrogen has 1. Okay, so 1 valence electron each for hydrogen, which means that our total number of valence electrons is going to be 4 times 1, or 4 plus 1 times 4. Which means we have to account for 8 valence electrons in this structure. We're going to next identify the central atom. Central atom in this case is going to be carbon because it's the only atom that's not hydrogen. Remember, hydrogen can't be a central atom in this case. We're going to then surround carbon with the ligands, which is the hydrogen atoms. I like to go in 4 corners. But again, it's in the end, we're going to talk about how these are rotationally dependent. So you don't have to really worry about where you draw these, but I like to go top and sides just because it looks better that way. I'm going to attach each hydrogen to the carbon with a single covalent bond, and I show that with a single dash. And now in this, I have used 2, 4, 6, 8 valence electrons. So I've used 8 valence electrons here. Well, I only had to account for 8 valence electrons, which means I have now used all of my valence electrons. That's great. I need to do a couple of quick checks though, because I need to make sure that all of my atoms have full valence shells. Now, hydrogen only requires 2 valence electrons for a full valence shell. If I look at each hydrogen, it has a single bond attached. Each single bond contains 2 valence electrons. Therefore, each hydrogen has 2 valence electrons, therefore a full valence shell. That is good. The carbon needs 8 valence electrons to fill its valence shell. Therefore, it has 2, 4, 6, 8, and it has a full valence shell. Therefore, this structure of methane is complete and is accurate given the information that we have regarding the number of electrons and the configuration of the molecule. The second molecule we're going to look at is also fairly straightforward, but it does build in a little bit of complexity, and that's going to be the molecule ammonia, NH3. Just like in the last problem, I need to make sure I account for every valence electron. Nitrogen has 5. Each hydrogen has 1. So 8 valence electrons need to be accounted for in this structure as well. In order to do this, I'm going to look for the least electronegative atom that's not hydrogen. In this case, it is nitrogen, the least electronegative that's not hydrogen. That's my central atom. Draw the ligands around it. And complete this process by adding a single bond between each hydrogen and the nitrogen. Now you'll notice I've only added 3 bonds here. 1, 2, 3. That accounts for only 6 valence electrons. Remember, valence electrons, all right, in bonds, there's 2 valence electrons in each bond. Therefore, there have only been 6 bonds represented here. I have 2 remaining. Oops. There's 2 electrons left. Where do they go? Well, remember, the next step is to look and add them to the central atom, in this case, the nitrogen. Now, this is the first time you will have seen a lone pair of electrons. And a lone pair is also known as an unbound pair or an unbonded pair of electrons. These are electrons which are not associated with a covalent bond. Now, nitrogen in this case has 3 pairs of electrons that are in single bonds, and this 1 pair of electron at the top that is an unbonded pair or a lone pair of electrons. In order to assess whether my structure is accurate, again, I want to double check to make sure that every atom has a full valence shell. In order to do this, I'm going to take a look and say, okay, hydrogen needs 2, and each hydrogen has 2. 2 being within each single bond. The nitrogen needs 8, and it has 2, 4, 6, 8. It has 8. Remember, each bond represents 2 electrons, and the lone pair, each electron is actually physically represented in the diagram. So the nitrogen has 8 valence electrons, therefore a full valence shell. Therefore, this is my completed diagram for ammonia NH3. Let's do one more example. All right, that's a little bit more complex, but still not terrible, and that's going to be carbon dioxide, CO2. Carbon dioxide has some additional complexity, so let's build these in as we go, but we're going to go through the same process still the same way. First thing I need to do is count the number of valence electrons. Carbon has 4. Each oxygen has 6. Therefore, we have to account for 16 valence electrons total. The central atom in this case is going to be the carbon. It's the least electronegative atom. If you look at the periodic table, remember, electronegativity is based off of effective nuclear charge and number of energy levels. Carbon and oxygen, same number of energy levels, but oxygen has an effective nuclear charge that is +2 greater than that of carbon's. So carbon is less electronegative. Carbon's going to be my central atom. I'm then going to draw the 2 oxygens on opposite sides of the carbon as my ligands. Connect both with a single bond to the carbon. Now that accounted for a total of 2 electrons per bond. So that's 4 electrons that I've accounted for. I have 12 remaining. Where do those go? Well, I'm going to start by filling the valence shells of my ligands. In this case, the ligands are oxygen. Oxygen requires a total of 8 valence electrons to have a filled valence shell. So I can add 6 more electrons to each oxygen. 6 electrons to each oxygen will bring them to a total of 8. So now what I've done is I've accounted for every one of my valence electrons. That's great, but I need to double check to make sure that my valence shells are all filled of all atoms. I know the oxygens are. 2, 4, 6, 8, and 2, 4, 6, 8. But the problem is carbon only has 4. Now that's not a full valence shell for carbon. So that's not a precisely, or it's not an accurate Lewis structure yet. It's not correct yet. We need to go through the next steps. And remember, this is where we deviate from reality. This is not what's actually happening in nature. But what I'm going to do is I'm going to identify the fact that if I pull 2 electrons from this oxygen here and add them as a double bond, what I've effectively done is kept oxygen with 8 valence electrons, 2, 4, 6, 8, because each bond represents 2. And the carbon, should I say now, has 2, 4, 6. See how I've essentially added 2 electrons to the carbon? Again, this is not what's happening in nature. Oxygen does not give 2 more electrons to the carbon. That is not happening. But this is how we diagram it to be as precisely accurate as we can. Okay? But the carbon's still not good yet. It still has 6. It needs 8. So I'm going to do it for the other oxygen as well. And now if you look at it, carbon has 2, 4, 6, 8 valence electrons, and each oxygen has 2, 4, 6, 8, and 2, 4, 6, 8 valence electrons. In this case, all atoms have full valence shells, and therefore this is the final diagram of the molecule. In a future video, I'm going to show you why we did double bonds to both of these and not a triple bond to one and a single bond to the other. But again, we're going to get into that in a future video. All right, so the final structure we're going to deal with today is a tricky one. And the final structure is going to be that of NCS minus. It's an ion. Now, NCS minus. Now, if we look at this molecule or this ion, you need to understand a couple of things. First of all, we need to still do the same process. Even though this is the most complicated structure we've seen yet, we go through the same exact process. Count the number of valence electrons first. Nitrogen has 5, carbon has 4, sulfur has 6. But be careful. That minus charge, remember, that means it has 1 extra electron, which means we add 1 more. Okay? If it's a positive ion, we subtract 1. But in this case, it's a negative ion, so we add 1. This means we have to account for a total of 16 valence electrons. The central atom is that of carbon, because it's the least electronegative atom between carbon, sulfur, and nitrogen. Carbon's the least electronegative. So nitrogen and sulfur are going to be on opposite sides of it, and connect them with a single bond. That's 4 electrons used. I have 12 remaining. 12 electrons left. Now, the way I'm going to go through this is by saying, okay, well, if I have 12 electrons remaining, how am I going to be able to appropriately create this structure? Well, I'm going to go through the same process we did with carbon dioxide and the others. I'm going to finish the valence shells of my ligands. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That gives each of the 2 ligands 8 valence electrons. And in the meantime, it also used all of my valence electrons. Okay? But just like in the last one, carbon doesn't have a full valence shell. So what I'm going to do, remove 2 electrons from the nitrogen, put them in a double bond, remove them from the sulfur, put them in a double bond. Now, what makes this one extra step is remembering that this is an ion. So what I need to do is bracket the entire compound and add that negative charge at the top. That's going to give me this overall Lewis structure of NCS minus. All right, that wraps up today's video. Let's go ahead and recap the fact that we learned today how to draw simple Lewis structures. And we did so by building 4 different molecules with essentially the same set of techniques, right? We have the same list of steps for any molecule or polyatomic ion that we're going to be drawing using a Lewis diagram. And we go through the same process each time. All right, so whether we're dealing with methane or ammonia or carbon dioxide or a more complicated polyatomic ion, the process really doesn't change. As we go forward, we're going to build that complexity out by adding in some unique qualities to molecules that were not present in these molecules themselves. So I hope you enjoyed this video, and I'll see you in the next one.